Hello. Today I will be talking about geospatial data models. This is an incredibly important topic to understand GIS. And if you missed class with me where I gave the lecture in person, I strongly recommend that you at least skim the Bolstad chapter on Blackboard. If not, read it more carefully. This is an important concept here to understand how GIS data is formatted and saved. Okay, so there are kind of three primary data models. In reality, there are really two: vector and raster-based data models. For the most part, we have only discussed vector data models. Raster are the other really common data model that we'll talk a bit more today. And then we will basically not talk about TIN models at all, but helpful to kind of know that they're still around. Okay, so to jump right in, vector data models, like I said, are what we're most familiar with. This is kind of what we've done in Google Earth with points, lines, and polygons, where you basically drop a point. It has a particular latitude and longitude, and it's a coordinate, right? And that's as simple as a point is. And a line is simply a series of points. And I think you all remember, creating those lines in Google Earth, and that's literally what the line is. It's a series of points connected with straight lines. So you have a beginning node and an ending node, and then each individual point here is called a vertex, and plural of vertex is vertices. And so you have a series of vertices and the straight lines that connect them, and that kind of makes up your line. And an area is kind of an extension of that when you make a polygon or an area. It's a series of points that compose a series of lines, and then the last node, there's a line that connects the final node to the beginning node, again in a straight line, and that encloses an area, and that's our polygon. A raster data model is entirely different. A raster data set is like a piece of graph paper. And the kind of objects of interest would be individual grid cells that are kind of highlighted or have different values than other grid cells. And you can still kind of characterize or capture points, lines, and kind of area within a raster data set, but it looks fairly different than that it is in the vector data model. And we'll get into this a bit more detail. Okay, so back to that vector data model. As we said, we have these coordinates that are used to define the boundaries of a particular feature. So in the example of polygon 1 here, which is Turtle Lake, you can see that they define the edge of the lake and the islands in the interior. And then that feature can have attributes. And so this polygon number 1 has 3 attributes. It has a name, Turtle Lake. It has a land use type, park. And it has an area, 102 hectares. The connection between spatial and non-spatial data are made through database tables. We call them attribute tables. We've talked about that a little bit before. And it's important to note that the vectors are meant to define discrete features, right? This is not necessarily for continuous environmental variables or non-environmental variables. It's not meant for continuous kind of things. It's meant to define discrete features that are, points within the environment. That are points or that are lines like a river or a road or a boundary, or that are polygons, buildings or areas, right? Or lakes. So vectors define kind of these discrete discrete items in space. And it's important to know that we cannot attach attributes to particular vertices, right? The attributes are attached to the feature itself, whether it's a point, if it's a point data set, or you attach it to a line or to the polygon. Attributes cannot be attached to individual vertices that would make up a line or a polygon. And then just kind of a little bit more detail about how these, particularly the line and the polygon are kind of saved or stored, is that we have each line is kind of would be decomposed into smaller segments of lines. So you might have that whole where's my cursor? You can't really see it. There it is. Okay, so here we've got line ID 11, and it begins at node 10, 1, sorry, and it ends at node 4, right? So you can see that over here. And this whole line would be made up of those kind of three segments of line. And a polygon then would be made up of kind of segments of lines that themselves are composed of kind of several vertices. Right? And now the lines can be as simple as two vertices, a beginning node and an ending node, and a straight line that connects between the two of them, or it can be as complex as hundreds of thousands of vertices, something incredibly complex. And the same can be kind of said for polygons. It can be very, very simple. I guess the minimum would probably be three vertices. Or incredibly complex and incredibly detailed. So they can kind of run that whole spectrum. And when we talk about attribute tables, we need to we can think of it kind of like an Excel table. And in fact, you can actually read these in Excel. You can actually open these up in the Microsoft Excel program and read them almost the same as you would read them within the ArcGIS program or within Arc programs. And so these attribute tables are made up of a series of rows, and a row consists of a set of attributes. And so these columns are attributes, and they must have the same type within the entire table. So one column or one attribute must be of a particular type, and I'll explain that in just a second. The field is at the top, and that's kind of the name of that attribute, or it just kind of describes what that column or attribute is. And it's important to note that all rows in the table must have the same set of fields. They must have the same set of attributes. Okay, you can't have one particular row, one particular feature in your database, in your vector data set that has an attribute of hair color, and another feature or another row in the same data set that does not have that attribute but has the attribute height. Right? That's not possible. And it's important then also to note that attribute tables so that the actual kind of value stored in the table can be any number of things. They can be text, descriptive string of text. They could be coded values, numeric values, so just a real numeric value. So a bunch of kind of numbers here, and importantly, an object identifier. Often either the field name is either FID or OID, and those are unique and cannot be changed or deleted, and they relate to each specific feature. I'm going to run through this very, very quickly here. Topology. It's a set of rules and behaviors that model how points, lines, and polygons share coincident or overlapping geometry. It allows us to control spatial relationships between features. Generally, this runs in the background. You don't have to control this, but in some cases, you may want to. For instance, you could this topology rule would be that no polygons should be overlapping, right? Let's think, you know, lakes. You can't have two lakes that overlap each other, or say property or state boundaries. You can't have part of North Carolina be within South Carolina, right? And so if, as you were drawing these two boundaries or polygons, and they happen to kind of cross over each other, then this topology rule would flag that as an error, and it would help you kind of eliminate those mistakes. And there are other types of topology rules too. Like I said, you really don't need to know too much about this, but it's important to know that it exists. And as you move kind of more into more complex GIS, you can use this to your advantage. Data has a one-to-one relationship between the entities and the objects in a layer. So there's typically one feature or one row within the attribute table relates to one feature in space, typically, but that's not always the case. All right, I'm going to actually end here before I jump into talking about raster data, because I'm going to need at least a couple more minutes to do that. So this lecture will be continued in a second video. Thanks for listening.